Good afternoon, everyone. This is Dr. Shujian Chen from the University of Queensland. It is my pleasure to present here as a researcher under 35. Today, I'm going to present our recent study about damage-tolerant building materials. In today's talk, we will focus on how to borrow ideas from the exoskeletons of animals to make materials more damage-tolerant. Today's talk will be based on our recently published article on Nature Communications. If you want to learn more details after today's talk, please refer to this article. The link of the article will be given at the end of the presentation. The study has raised wide media attention and has been reported in over 100 different news releases, so you might have read about a brief story of our study, but here we will share with you some more interesting facts and ideas behind our study. We can begin by looking at the structures hidden in natural materials. We are talking about natural materials produced by living creatures to build functional structures in order to survive. For example, the shells of oysters, crabs, and shrimps, the spider's silk, the scale of fish, and the carapace of turtles and tortoise are all made of natural materials. While many of these natural materials sound quite familiar, very few people know about the structures hidden in them. Most natural materials have some sort of structure in them. There are over 7 million different living creatures on Earth. Based on the studies conducted in the past several decades, most of the natural materials are found to be built from 8 different basic structures. These 8 basic structures are listed here. The basic units of these structures, or in other words, patterns, are also called design motifs. Here, we will look at a few basic structures, in other words, design motifs, that can effectively increase the damage tolerance of materials. One of the most studied is the layered structure. They commonly occur in shells. If we zoom into the inner layer of the shells, we can find a thin layer called the nacre layer. More than 97% of the nacre is made from brittle calcium carbonate tablets, as shown in this figure. Calcium carbonate is the primary constituent of limestone. Limestone, like most types of rocks, is quite brittle. If you have a piece of limestone as thin as the shells and you bend it, it will just break immediately. However, the shells are much more flexible and robust. Nacre is about 3,000 times tougher than limestone. While nacre and limestone are mostly calcium carbonate, you may wonder why nacre is much tougher and damage tolerant. The secret lies in the thin layer of flexible biomaterials between those calcium carbonate tablets. When nacre is stretched under tension, these flexible layers allow the tablet to slide along each other. The sliding process generates a strong frictional force without breaking those tablets, so the material can carry tension force when these tablets are sliding. Mantis shrimp is another marine animal with unique structures. Mantis shrimps can deliver some of the hardest punches in the world. The speed of mantis shrimp punches can reach 23 meters per second. They use their punches to crack the shells and prey on them. The heat is so powerful, and it not only cracks the already strong nacre structure, but also causes the water around them to boil. If we take a closer look, at the clubs of the mantis shrimps, which is used to hit its prey, we found that under a microscope, there is a helical structure in these materials. Such structure is similar to the layered structure in nacre, but instead of using tablets, it uses layers of mineral rod arranged in a spiral shape. The helical structure is highly effective against cracking under impact, because cracks need to go through the weaker interface between the stiff rod in a twisted path. The energy absorption during this process is significantly increased. In summary, by using various types of structures, natural materials usually perform much better than the minerals within them. The basic unit for these structures is called the design motif. As shown in the graph here, a design motif is a basic pattern that can be duplicated to form a bigger pattern. This is a suture structure that can also increase damage tolerance of materials by allowing sliding and friction at these interfaces. Moreover, many design motifs can be combined at different scales to optimize the performance. For example, this figure shows the structure of the bones. We can see that it combines such tubular structures and cellular structures ranging from nanometer level to millimeter level. So far, we have gone through some of the design motifs discovered before our study. However, as many of you may have noticed, none of the 8 types of motifs is effective for damage tolerance under compression. All 3 damage tolerant structures, layered, helical, and sutures, are primarily effective for tension, or in other words, for stretching. Because we are civil engineers, many of the brittle materials we use, such as cement and concrete, are mainly used to carry compressive load. So our team has set on a journey to search for an undiscovered design motif for compression. After searching and researching for a few years, we have discovered a new design motif that can be extracted from the legs or feet of fleas. Flea is known as one of the best jumpers. If a flea is the same size as a person, it can jump up over 150 meters. For someone to jump so high, their legs and feet must bear a large compression force. Based on the impulse and momentum theorem, this force is the same as the force on our legs when we fall from a height of 150 meters and then land on the ground. So how do fleas prevent damaging their legs when jumping? We look into the structure of the flea's feet and legs and find that the segments played the key role. The remarkable thing about these segments is that it can only rotate in one direction, as shown here. As shown in our figure, one side of the structure is made of rigid blocks, and the other side is made of a flexible band. So when the band extends, the flea's leg and the segments will straighten and become strong in compression. When the compression force is too large, the band will retract and the block will bend. This bending can buffer the force and prevent further damage to the segments. Searching for a suitable design motif from so many different species is challenging, but it is even more challenging to develop a way to fabricate these structures into materials. We started our experimental trials by trying to replicate the segmental legs using cementitious materials. We used 4 categories of new techniques to achieve this. First, we used high-resolution 3D printing to produce a polymer scaffold. Then we found some method to design the cementitious material before they turn solid, so the cementitious fluid can form the shape we want. To mimic the multi-scale structure in natural materials, we used nanoengineering and machine learning to optimize the microstructure of cementitious materials. We call the new method used here the scaffold and fluid method. The basic idea of the method is to coat a flexible polymer scaffold with cementitious fluids. The scaffold is designed to exploit the surface tension and rheological properties of that cementitious fluid, so we can make the cementitious structure with complex shapes at micrometer level. In this case, we used this method to fabricate the segments. But this method can also fabricate other complex structures using materials such as cement. In addition, this scaffold will function as a sensor. When the maximum capacity of hardened cement is not reached, it needs to keep the cement segments straight so it can carry compression force. When the maximum capacity is exceeded, the scaffold needs to retract and facilitate the rotation of the segments. As addressed earlier, natural materials are excellent in terms of performance because they have structures from nanometer scale to micro and millimeter scale. Similarly, we can use nanoengineering to alter the microstructure of cementitious materials. One example will be the use of graphene oxide. Adding graphene oxide to cement paste can reduce microscale pores, which are the blue and green pores here, to nanometer pores, which are red and purple. As the pore size reduces, the performance of cementitious materials will typically be increased. However, to optimize our material, we not only need to look at how to reduce pores and refine the microstructure, but also need to understand which type of microstructure can perform the best together with our segmental structure. That is why we started investigating how to understand nanoscale structures of materials like cement binder. On the screen are many microscopic images of different nano-engineered cement binders. These structures are traditionally considered to be disordered. Being disordered means the microstructure is random without any describable patterns. We have developed new techniques to quickly obtain thousands of images of nanostructures, which allow the use of machine learning to analyze and understand these disordered structures. We find there are actually some patterns in these disordered structures, which makes some cement binder better than the others. These categorization techniques help us to improve the performance of these segments. Just now, we have covered how to replicate individual segmental legs using a combination of various techniques. Based on different applications, we can also assemble the legs into columns, lattices, and forms as shown here. As our primary goal is to tackle the problem of the brittleness of many construction materials, such as cement binder and concrete. We focused on assembling this type of honeycomb material using the segmental legs. In this structure, the edges of all the legs are connected and bracing each other. Also, all the legs are aligned vertically to ensure the best performance under uniaxial compression. If this material is loaded under compression, it's 200% stronger than traditional lightweight cementitious materials. As we can see from this figure, When the force is too large, the top layer segments will rotate, while the rest of the layers remain intact. This asymmetrical rotation makes the material very damage tolerant. It can maintain 80% of its strength when squashed to less than half of the original length. Such properties will be very beneficial for building material applications. In the current practice, we have to use a capacity reduction factor of about 0.6 to prevent brittle compression failure of concrete, which means that 20 to 25% of the material capacity is wasted due to the brittleness of concrete. Addressing the problem of the brittleness of building materials can therefore lead to significant savings in the use of cement and, of course, the CO2 generated from making cement. Our study found that after adding the segmental design motif to brittle materials, the structure built with these brittle materials can perform better than those built with ductile materials. As shown in the figure here, this structure is subjected to impact. The left-hand side, made of segmental materials, can have significantly lower residual stress and less damage compared to the right-hand side, which are made of ductile materials. Finally, I would like to share some of our thoughts about the nanoengineering of cementitious material in the future. In the past 2 decades, most of the research focused on effectively mixing nanomaterials with cement, which is the so-called dispersion problem. With the effort of many researchers worldwide, the dispersion problem is largely solved. We believe that in the future, people will be more interested in how to design and engineer the most effective disordered structure from the nanoscale. Here are 3 key questions our team would like to share with everyone, and we would be flattered if you could share your thoughts with us in the future. These questions include how to discover and understand patterns in disordered microstructures, how to evaluate material performance based on disordered microstructure, and how to improve performance of disordered microstructures. If you want to check out some more details about the methods we used, you can visit the given links here. Thank you for your attention and see you next time.